This is episode 7 of the Key Concepts in MySQL Group Replication InnoDB Cluster podcast. Welcome to the deep dive. Our goal here is always to take these sometimes pretty complex tech topics, break them down, hopefully give you those aha moments, make it clear, make it actionable. Today, we're really digging into MySQL Group Replication, and this isn't just like a small feature update. It's a pretty foundational shift for database high availability, for consistency. It's also part of our ongoing series, so we're building on some things we've touched on before. So what's the plan for today? What are we covering? First, we'll look at what really makes group replication fundamentally different from, say, traditional setups. Then we'll explore its nervous system, the group communication system, or GCS. We'll also need to understand the sort of universal receipt for transactions. Global transaction identifiers, GTIDs, super important. After that, we'll see how it smartly handles conflicts using certification without needing a central manager. We'll compare the operational modes, single primary versus multi-primary. What are the trade-offs?
And finally, we'll cover automatic recovery, how you can fine-tune consistency levels, how it manages flow control to keep things in sync, and importantly, how it handles network partitions. By the end of this, you should have a really solid grasp of these core ideas, enough to understand how you can build these really robust, highly available MySQL systems.
Right. And it's worth mentioning that a lot of the core technical grounding for our discussion today comes from the excellent resources over at kedar.nitty-witty.com. It's been a really valuable guide for us putting this together.
Okay, so let's jump right in. That core difference.
Yeah.
When we think replication, often it's that classic master-slave picture that comes to mind. Feels like one person telling a story, everyone else just listens and copies it down. But group replication, you said, it's a whole different beast, isn't it? More like a committee where everyone has to agree.
Exactly. That's a great analogy. What's really fascinating architecturally is the move away from that master-slave model entirely. It's a shared nothing, peer-to-peer setup. Every node in the group is essentially equal. And the revolutionary part, I think, is embedding a consensus protocol. It's a Paxos variant directly into the database layer itself.
So it's not just bolted on.
Not at all. This means data consistency isn't an afterthought. It's baked right in. A transaction only commits if a majority of the group agrees. This inherently prevents those split-brain problems and guarantees everyone sees the same data. It's really a shift from just replication to a truly coordinated cluster.
You mentioned consensus, and that immediately brings us to the group communication system, the GCS. You called it the nervous system. What's it actually doing under the hood? How does it enable that coordination?
Well, think of GCS as this incredibly reliable, like a specialized postal service just for the database cluster. It uses a component called XCom. And XCom doesn't just make sure messages get delivered, it guarantees they're delivered in the exact same order, totally ordered to every single member.
And that totally ordered part sounds absolutely critical.
Oh, it is. It's non-negotiable. For every transaction to end up with the identical data state on every node, the operations have to be applied in precisely the same sequence everywhere. There's just zero room for error on that. Perfect order is fundamental for data integrity.
Okay, so we have reliable, ordered communication. But how does the system keep track of the actual changes, the transactions themselves? That brings us to GTIDs, right? Global transaction identifiers. These aren't just a nice-to-have feature, are they? They seem central.
Absolutely central, not optional at all. GTIDs are like that universal, unique receipt or barcode for every single transaction that modifies data. Each one gets a distinct ID based on the originating server's unique ID, its UUID, and a sequence number. Think of it like server-UUID.transaction number, globally unique.
And what do these unique IDs enable?
They play several critical roles. First, conflict detection. They uniquely identify transactions that might be trying to change the same data concurrently. Second, recovery. If a node goes offline and rejoins, it uses the GTIDs it has already processed to figure out exactly which transactions it missed. Allows for a really seamless catch-up.
Okay.
And third, just tracking. It gives you a clear, unambiguous audit trail of every data change across the whole cluster. Very powerful.
Right. So speaking of conflicts, this is where group replication gets really interesting for me. It uses this certification-based conflict detection. How does it manage conflicts without needing some central lock manager, which, as you know, can often be a bottleneck?
Yeah, the mechanism is actually quite elegant. It avoids that central bottleneck. Here's how it works. Before a transaction even tries to commit locally, it first broadcasts what's called its write set to the entire group.
The write set. What's that exactly?
It's essentially the unique list of rows, identified perhaps by their primary Ps, that the transaction intends to modify, like a declaration of intent.
Okay, so it declares what it wants to change, then what?
Then every member in the group acts like a detective simultaneously. They synchronously check if this incoming transaction's write set clashes or conflicts with the write set of any other transaction that's currently in flight or has already been certified by the group.
Ah, so it's a group effort to check for conflicts.
Exactly. And if any member detects a conflict, say, two transactions trying to modify the exact same row at the same time, the incoming transaction is immediately rolled back on the node where it originated. It never even gets applied anywhere else.
And this happens before the commit.
Precisely. That's the key takeaway. It's a synchronous check before the commit happens anywhere. It's not some messy cleanup operation that happens asynchronously later. It's all about preventing inconsistency from ever occurring, rather than trying to fix it after the fact. That ensures data consistency right at the core.
That makes sense. It sounds much cleaner. Now, group replication offers two distinct ways to operate: single primary and multi-primary modes. Let's start with single primary. I hear that's often the recommended starting point for many use cases.
That's generally true, yes. In single primary mode, it's quite straightforward. You designate one node as the primary. Only this node handles write operations. All the other nodes in the group act as read-only secondaries, just applying the changes replicated from the primary.
Kind of like having just one person with a pen in a meeting, to use that analogy again.
Exactly. It simplifies things considerably because you inherently avoid write conflicts between nodes. Since only one node accepts writes, there's no chance of two nodes trying to write conflicting data simultaneously.
So the main pro is simplicity and stability. Any cons?
The potential downside is that the single primary node can become a performance bottleneck if you have extremely high write traffic. All writes have to go through that one server, but, and this is important, it's not a single point of failure for availability, because if that primary fails...
Ah, yes, the automatic failover kicks in, which we'll get to.
Right. Another node will automatically be elected as the new primary. So availability is maintained, but write throughput is limited by that one node's capacity.
Okay, so that leads us naturally to the alternative for those who need more write capacity. Multi-primary mode. What's the story there?
Right. In multi-primary mode, the restriction is lifted. Every node in the group is effectively a primary and can accept write operations directly.
So potentially higher write scalability.
Potentially, yes. It can distribute the write load across multiple servers, and it means your application doesn't necessarily need complex logic to redirect writes if one primary fails. It can just write to any available node.
Sounds great, but I sense a but coming.
There is a significant but. Your application must be designed to be conflict aware, because now you can have conflicts. Two different nodes might accept transactions that try to modify the same data concurrently.
And how are those conflicts handled?
When a conflict is detected during that certification process we talked about, the rule is typically first committer wins. The transaction that reached the certification phase first gets approved, and the conflicting transaction gets rolled back.
A rollback, not a merge or anything complex.
Correct. It's a rollback. So your application needs to be robust. It needs sophisticated error handling to catch these deadlocks or transaction rollbacks and retry them gracefully. You also often need careful schema design, maybe using things like auto-increment offsets per server or application-level sharding strategies to actively minimize the chance of conflicts occurring in the first place.
So multi-primary offers more write power, but demands more from the application and database design to handle the complexity.
Precisely. It's a powerful option, but definitely more advanced and requires careful consideration. Single primary is often simpler and safer to start with.
Okay, let's talk about one of my favorite features, something you alluded to earlier.
Right.
Automatic recovery, specifically the automatic primary election in single primary mode. Can you paint a picture of what happens when that designated primary node just vanishes? Maybe the server crashes.
Yeah, it's pretty seamless, actually. Picture this. Your primary node suddenly goes offline. Poof. In a more traditional master-slave setup, this might trigger pager alerts, right? Someone gets woken up at 2 a.m. to manually promote a slave server.
Been there. Not fun.
Right. With group replication, it's completely different. The surviving nodes in the group notice the primary is gone. They communicate amongst themselves using that same GCS and consensus protocol. And they basically hold a quick, automated election. They say, okay, the boss is gone. Who's next in line based on our criteria?
And this happens automatically. No scripts, no human needed.
Completely automatic. The election process is very fast, usually just a few seconds. A new primary is chosen from the available secondaries, and the cluster continues accepting writes on the new primary. It's a fantastic demonstration of true high availability baked right into the system, minimizes downtime drastically, and removes a common source of human error during stressful failover events.
That set it and forget it aspect for failover is incredibly appealing. Now, for the listeners who like to tinker and optimize, let's talk about consistency tuning. There's this variable, group replication consistency. Sounds like a consistency knob. How does that let you balance consistency guarantees versus performance?
Exactly. It's like a dial you can turn. It addresses the question. How strictly consistent do you need your reads and writes to be across the entire group at any given moment? Because stronger guarantees often mean slightly higher latency. You have 5 different levels you can set, usually per session. They range from eventual, which is the fastest but offers the weakest guarantees.
Weakest meaning.
Meaning a read on a secondary might see data that's slightly older than the absolute latest commit on the primary. It'll get there eventually, hence the name. This is often the default.
Okay, and at the other end?
All the way up to before and after. This is the strictest level. It basically ensures that reads, before, see the effects of all preceding transactions across the group, and writes, after, are visible on all members before the transaction acknowledges success. It provides the strongest possible guarantees, globally ordered read-write operations, but it's also the slowest because it involves more coordination weights.
And there are levels in between.
Yes, like before, which guarantees reads see the latest data, or after, ensuring writes propagate before acknowledgement. There's also before on primary failover, specifically designed to prevent reading stale data right after a new primary takes over. So you can choose the level that makes sense for specific parts of your application, balancing the need for strict consistency against performance requirements.
That flexibility is really useful. Okay, another practical concern. Keeping nodes in sync. What happens if one node in the group starts lagging behind in applying the replicated changes? Does it just fall further and further behind? That's where flow control comes in, right?
That's exactly what flow control is designed to prevent. You don't want a member lagging too much, as it could affect read consistency and potentially lead to the node being expelled if it falls too far behind. Think of flow control as like the traffic cop for the replication stream within the cluster.
A traffic cop. How does that work?
The group constantly monitors the replication apply queue on each member. Basically, how much work is piling up for each node to apply. If one member's queue, the slowest member's queue, exceeds a certain configurable threshold, the group proactively starts to throttle the rate at which new transactions are admitted into the group and certified.
So it slows down the writers to let the slow reader catch up.
Essentially, yes. It applies back pressure. What's interesting is that it's proactive. It doesn't wait until the lagging member is hopelessly behind or causing major problems. It intelligently slows things down just enough to allow that straggler to catch up gracefully without necessarily halting the entire cluster.
That sounds more nuanced than some other systems.
It can be. Some other distributed database systems might employ more aggressive, cluster-wide flow control that could pause writes across all nodes temporarily. Group Replication's approach aims to be a bit more surgical, throttling based on the capacity of the actual bottleneck member.
Got it. Now, related to nodes joining or rejoining, especially if they've been offline for a while or brand new, we need an efficient way to get them the current data. You mentioned recovery earlier. Is there a modern way besides old school backup and restore?
Oh, absolutely. For efficient provisioning and recovery, especially for large databases, the clone plugin is really the way to go now. It's a game changer compared to older methods.
The clone plugin, what does it do?
Think of it like a professional moving service for your entire database instance. Instead of the often slow and cumbersome process of taking a backup on one node, transferring it, and restoring it on the new node, the clone plugin lets a joining node directly connect to a healthy donor node in the cluster and physically copy the entire data directory across the network.
A direct physical copy?
Yes, it copies the data files directly. This is usually much, much faster than logical backup and restore, especially for terabyte-scale databases.
And more automated?
Significantly more automated. It integrates smoothly with Group Replication's joining process. It's a really critical part of the whole self-healing aspect. The cluster can effectively provision new members or recover failed ones much more quickly and with far less manual effort. Saves a ton of time and potential errors.
That sounds incredibly useful for scaling and maintenance. Okay, let's tackle one final really critical topic for any distributed system: network partitions. This is the scary scenario, right? What happens if network problems temporarily split your cluster into 2 or more isolated subgroups that can't talk to each other?
Yeah, this is where the underlying consensus protocol really proves its worth. It's fundamental to handling partitions safely. When a network fault occurs and divides the nodes, the group's built-in intelligence kicks in. Only the partition, or subgroup, that retains a strict majority of the original group members defined as more than half, N2 plus 1, is allowed to continue operating normally and accepting write transactions.
Only the majority partition keeps working. What about the others?
The minority partition, or any partition that doesn't have that strict majority, automatically recognizes its status and puts itself into a read-only mode or blocks writes. It stops accepting any new write transactions.
Why is that so important?
This is the built-in safety mechanism to absolutely prevent the catastrophic split brain scenario. Split brain is where you have two independent parts of your system, both thinking they're the active primary, accepting conflicting writes, leading to divergent data, and a nightmare reconciliation task later. Group replication's majority rules approach guarantees this can't happen. It ensures there's always only one single authoritative view of the data, even during network failures.
So it prioritizes consistency, even if part of the cluster becomes unavailable for writes.
Exactly. This firmly places group replication in the C-key category of the CIP theorem. It prioritizes consistency and partition tolerance, potentially sacrificing some availability in the minority partition during the network split to guarantee data integrity. For most critical systems, that's the right trade-off.
That's a crucial guarantee. So, wrapping things up, if we step back and look at the bigger picture.
Yeah, if we connect all these pieces, MySQL Group Replication really provides this robust, quite comprehensive solution for achieving both high availability and strong data consistency. We've seen how its architecture based on consensus, its smart way of handling conflicts before they cause trouble, and its automatic recovery mechanisms fundamentally change how we approach building resilient database infrastructures. It's a big step beyond traditional replication methods.
So, boiling it down, what does this really mean for you, the listener? Well, whether you're managing those absolutely mission-critical applications where downtime is unthinkable, or maybe you just want better peace of mind about your data's consistency and availability, Group Replication gives you the tools. Tools to build systems that aren't just highly available on paper, but are genuinely self-healing and consistently reliable in practice. Like we said, it feels like a foundational shift, moving from just copying data around to having a truly coordinated, intelligent cluster that manages itself to a large extent. So here's a thought to leave you with. How could this level of built-in consistency, this automation, particularly around failover and recovery, actually transform your deployment strategies? Could it free you up from writing and maintaining complex failover scripts? Let you focus more on your application's features? What new possibilities does having such a reliable foundation unlock for whatever you're building next? We hope this deep dive was useful. Like this podcast if you found it valuable.
Please share it with colleagues, friends, anyone you think might benefit from understanding group replication better. And of course, don't forget to subscribe to the channel for more insights into database technologies and related topics. Thanks for listening.